Hi, everyone. Welcome to the North Central Climate Science Center. Welcome to the North Central Climate Science Center monthly check-in. Today we have Bill Parton as his speaker and as our speaker, and I'm actually going to let Dennis Ujima here introduce him.
It's my pleasure to introduce Bill Parton. We've been working together since probably around 82 or 83. And Bill is a well-known ecologist and developer of the Century model, now the daily version Descent, which we'll be talking about. And something of note about Bill's background is that as a world-renowned ecologist, ecosystem scientist, he has never taken an ecology class in his life. His background is really in meteorology, from his PhD in Oklahoma, or Penn State.
And Penn State.
And Penn State, both. And so, but through the years, and especially with the interactions here at the Natural Resource Ecology Laboratory, he's really absorbed enough ecology to really put one of the models together. And he's using this model now and components of this model to look at forecasting of grass productions. And so this is very germane to our sort of region of interest in the North Central Climate Adaptation Science Center. So Bill, why don't you take over?
Okay, so the goal today is to talk about this new model that we developed, which we call the GrassCast model. And the goal of the model is to make predictions of basically grassland plant productivity. And we start in the spring, like the middle of April, and make forecasts that hopefully the ranchers can use to make decisions on how to manage or how many cattle to have, and basically help them make decisions. And we want to make predictions for all of the Great Plains counties, or we are making predictions about how much grass production they will get at the county level. At the moment, it's at the county level. So it's not at the kilometer level, which we hope to do next year. But so how did we develop this GrassCast model? Basically, there are sort of like, you might imagine a stool. There are three legs to the process that we did. One of them is we took remote sensing data and that's, so we have the remote sensing data from basically from 82 on with the AVHR NDVI data at the county level. So we have this continuous representation of NDVI, the greenness index. And then we also have the Descent model predictions of actual evapotranspiration and all the rainfall related variables basically continuously, actually for the last 100 years. So we have a really long record there. So we have all the rainfall related stuff. And then we have really detailed plant production data sets for a given set of sites where we wanted to connect all of these three data sets so that we could predict plant production and the correlations of plant production to NDVI and the rainfall related variables. And then by doing these statistical connections, we now can make forecasts of plant production based on actually the bottom line. Simple answer for what we discovered is that the April through July cumulative actual evapotranspiration water loss, how much water the plants lose, is the variable that most controls plant production in the Great Plains. So if we can predict what that is, we can make a very good forecast of how much plant production we're going to get. The problem we have is getting rainfall forecasts that are worth anything. So, okay, let's go forward. Basically, I'm going to go through these three data sets, the three legs of my stool, and show how we use them to develop the correlations, basically, of actual evapotranspiration to plant production, actual evapotranspiration to NDVI, and then how we put that together to make these forecasts, the cast forecast. So next slide. One of the key things is we had to decide, or determine what are the variables that are most correlated to plant production. So we took these sites where we have 5 sites across the Great Plains, from a very dry site, the shortgrass steppe site, which has 300 millimeters, to the Kanza Prairie, which is 800 millimeters. So we wanted to look, what are the rainfall variables that are most correlated? And what we found, if you look at the triangle in the middle of the table, is that basically the April through July cumulative either rainfall or actual evapotranspiration were the variables most correlated to plant production. So we had like 40 years of plant production data sets at the Cheyenne site, and all these other sites had long-term data sets. So the bottom line at the site level analysis, that in general, AET for the April through July time period was the most correlated. But if you look at precipitation, it isn't that badly correlated. It's less correlated, but AET is more correlated. And the reason AET is a better variable is more theoretical, in that sense that what happens over the winter, how much snow you get, how much water storage is incorporated in the AET forecast, where if you just have precip, you know nothing about the winter time period. So I would be doing this anyway because it's theoretically a better thing, but we do find it's a better correlate. This next slide basically shows you model versus data for 2 sites, the Shortgrass Steppe site and the Cheyenne, Wyoming site. You can see the good correlation of plant production to cumulative AET. On the Shortgrass Steppe site, on the left, we have a low fertility and a high fertility site. The Owl Creek swale sites have high fertility, more production, and then the ridge and mid-slope sites have lower. The key thing there is that if you get more precip at the richer sites with more fertility, they actually have more of a response to increased precip. So at the landscape scale, you're going to see this variation in response, where we're looking at the county level initially and not looking at this finer scale pattern. But this is happening at the finer scale pattern. All right. One of the other big data sets we used is the NRCS ANPP, above ground plant production data sets. NRCS measures plant production, thousands of observations across the whole country, grasslands. The graph on the left shows the plant production based on NRCS at the county level. And basically you can see there's a north-south pattern. It's higher in the east. All the blue colors are high production, and then it drops as you go west, you get lower and lower production. So and that follows, if you look on the right figure, the pattern on actual evapotranspiration. So basically that's why we get this correlation of production to above ground productivity. And this is the mean long-term values here, not the seasonal variation. And if you do a statistical analysis, it ends up that AET is the best predictor for the long-term mean productivity from NRCS. So that again confirms our site level annual variability results. Next one is to get at how things might be different as we go from the wet regions in the east to the dry regions in the west. We've plotted at the CPER site, above ground production, AET, the red line for cumulative from April through July, and precip from April through July. And you can see they all three jump up and down, and they're quite variable across years. This is what you expect from a dry site, but there's this high correlation basically of all three of them together. You look at the Kanza Prairie on the right, and you look at the red line in particular, the same colors are there. There's hardly any variability in AET across time. So the reason, well, as I'll show, that as you get to the wetter sites, the variability in actual water loss becomes almost minimal in the wetter sites, where in the drier sites, we have really high variability. And we find that actually rainfall becomes more correlated to production in the wet sites rather than actual water loss. And so the AET actually is not at all correlated in the very wet sites in the eastern part, particularly in the really wet parts of the tallgrass prairie. So this correlation to AET actually falls apart when we get in the very wet part of the eastern part of the Great Plains. This next figure, I want to focus on the left figure and the right figure. The first thing on the left is a correlation between AET and precip. And you can see the strong blue color on the left, very high correlation, which is the graph I just showed before for the shortcut step, verifies that. But as you go farther east, you can see this correlation between rainfall and AET falls apart, where the R-squares actually gets less than 0.1 when you get to the eastern part. So rainfall and AET correlations disappear to a great extent as you get to the wet. And if you look all the way to the right diagram, I actually calculated the standard deviation divided by the mean for the same region. And again, you look at the red on the far east, and the standard deviation of AET actually becomes really small on the wet side and high on the western dry side. Rainfall in the middle doesn't show that strong pattern. So rainfall variability still has an east-west pattern, but not near as strong in the variability. And so the rainfall is still pretty variable across the whole region, where AET is not. It loses its variability in the wet sites. All right, so one of the key things, since we only have plant productivity for, say, 5 or 6 really good sites in the Great Plains, we really have to use NDVI if we want to extrapolate what happens spatially. And to prove that NDVI, the greenness index, actually represents plant productivity, we took the observed productivity for all these sites back to 82, and then with the remote sensing data on NDVI for those pastures where they were measured, and put it all together to develop this regression, which shows a 0.85 R-squares. And the key thing is it goes from the dry sites to the wet sites, and we have a relationship that predicts basically plant production as a function of integrated NDVI during the growing season. And it's the May through September integrated NDVI that we use we did in this regression. So we developed a regression that we now can use in our analysis to predict plant production as a function of NDVI. We also, because we were working at this large scale, we wanted to show, as you would expect, that the NDVI, since it's correlated to NPP, we should see a strong correlation with actual evapotranspiration to NDVI. So this figure gives the Laramie, Wyoming, or Laramie County in Wyoming, just north of us here in Colorado, correlation of actual evaporation to the NDVI. This is the AVHR data. So we can see again, we get a good correlation, and This is really, in our model, the core of what we do is we basically predict actual evapotranspiration, and then we go to this regression for Laramie County and say, okay, how much will the NDVI be for that county for that year? And then we use the previous curve to say how much plant productivity you get. So these two figures right here are the heart of the model. We use this curve to say, given the NDVI, how much production do you get? And this curve to say how much NDVI we have for the given amount of actual evaporation. So these are really the heart of the model. Well, to get AET, we use the DayCent model, which is a full ecosystem model. And it basically does many more things than anybody that we care about in this analysis. Basically, we predict methane uptake, methane production, nitrous oxide emissions, the full greenhouse gas balance for all ecosystems in the world are really utilizing this model. So we're only using this model to predict for grasslands. And the key reason we use this model is it does a great job of predicting actual evaporation and water balance for all of these ecosystems. So it's the use of the model to predict AET that we use in this analysis. The main inputs to the model are max-min air temperature on a daily basis and daily precip. So that's the only inputs it require, plus soil texture, basically. So it's a fairly easy number of variables available. Okay, how well does the model predict actual evaporation? We've got great data that's now available with eddy covariance sites. The top figure shows how well we predict daily AET at the shortgrass steppe for a particular year. Middle figure shows model versus data soil water. We can do a good job of that. And then we have data from the Kansa Prairie, which is the tallgrass prairie on the eastern side, and we're showing that we're getting the patterns, maybe not daily variations as well as we are at the shortgrass steppe, but we certainly get the seasonal patterns and the weekly patterns. So the DayCent model does a good job of simulating AET, which is the input to our GrassCast model. Okay. GrassCast project goals: predict total growing season above ground grassland production for all of Great Plains counties starting in the spring. And the key driver is the April through July cumulative actual evapotranspiration, how much water the plants lose. And we basically make these forecasts every 2 weeks. Key part of it is we use the real weather data up to the time that the forecast is given. So if it's April 15th, we can get the real weather data up to 2 days before that. So April 13th, we have what actually happened. And then we forecast forward what's going to happen. So that's unfortunately where we run into trouble, and I'll demonstrate when we look at our results from last year, where the forecasts were really off in the northern Great Plains. Okay, forecast procedure: use DayCent model to simulate 2018 county level AET. We do it actually for many, many different model runs. We actually do 36 model runs using historical data to project forward. So we use the real weather data up to the time we start, and then historical data to project forward, and we stratify that data by being normal, above normal, or below normal. And so we actually, not just one forecast, we actually are making 36 forecasts based on this. So we have diversity of forecasts, but we present the mean. So what we present to the ranchers is basically 3 forecasts: below normal, normal, and above normal, assuming that precip in the months following May, June, and July will actually be in those 3 categories. So we basically give the ranchers 3 maps to pick from and then decide, where they are in that category. Unfortunately, the CPC long-term forecast this year said all 3 of those are equally likely. So it doesn't really help the rancher. You have to sort of select where you are in those forecasts. But if we had a forecast that was accurate, we could really do a very good job of telling them exactly what's going to happen. That's the real challenge in the future. Okay, GrassCast forecast for 2017. So last year we started, and these are the results that we had. Last year we used the CPC forecast to actually predict what was going to happen. What happened is they predicted it was going to be above normal in the northern Great Plains continuously through the whole time period, from April, May, June, July. It was actually dry the whole time period, way below normal. So if you look on the forecast on the left, we do show it predicted being below normal. The yellows are below normal, reds are way below normal, and blues are above normal. So we're showing a pattern of potential low values in South and North Dakota. You look at the June 12th forecast in the middle, and that dry area, low production expands rapidly. And then you go all the way to June 30th, and we have a really, really low production in that region, which is what happened. The mid-Great Plains actually was above normal, particularly like southern Colorado into Kansas, and we had drought in the southern Great Plains. Interesting, this year, the southern Colorado and Kansas zone is dry, and where last year it was really the wettest. So you get substantial spatial patterns in these forecasts. How well did we do historically? 2002 was really one of the biggest droughts we ever had in the Great Plains. The NDVI data, which is an index of how production, you can see almost 90% of the counties were below normal production in that year. And you look at what we predicted, we were basically about 80% accurate in predicting what happens. So when we have historical data all the way back to 82 to verify how well the model works. 2009 was the opposite. It was wet everywhere in the Great Plains, and we predicted that pattern equally well. Okay. What do we forecast for this year? We started on April 22nd, and basically here's our 3 maps. On the left, it's below normal, assuming, so the lowest of the last 36 years, those are the driest 12. The 12 in the middle go to get our normal, and then our above normal is on the right side. And as you might expect, the difference between those maps is large because we're talking about everything from above normal to below normal. And but it does show, if you look at the normal to below normal, that parts of the North and South Dakota are potentially going to be below normal. And even the above normal forecast is not showing much potential in that region. So the northern Great Plains, at least in North and South Dakota, do not look good based on that forecast, where if you look in Montana, western Montana, actually the high and the normal show really good conditions, and they had good snows last year. So this is reflecting the overwinter snow. So and then the southern Great Plains, though, you look at the below normal, and they're all below normal productivity. This is what's happening there. We've had a major drought in that region. We were showing here in April that this is the most likely thing to happen. Even if you were above normal in Oklahoma, if you look at it, you would still be below normal in productivity. So the drought was, even with extra rainfall, you weren't out of it. So May 1st forecast, pretty much the same patterns. The central North and South Dakota do not look particularly good. But they did get some rain, so actually the Montana region's looking better. And the southern Great Plains is continuing to looks even worse if you have below normal. May 8th one, we continue the same pattern, the southern Great Plains, looking actually worse. But one of the things that happened in the middle of May is we started to get precipitation in the northern Colorado into Nebraska region. And we're actually seeing the potential for higher production in that region. And the western Montana region looks the same. Not much difference in the North and South Dakota region. Up to May 21st, again, the southern Great Plains patterns look the same. But one of the things that happened is the northern Colorado and Nebraska region is starting to look more promising. Southern Colorado and the southern Great Plains looks even, not improving at all. And in the northern Great Plains, not particularly big change. We did get in the June 4th basis, we're actually finding Montana looks even better. We got some really good rainfall in eastern Montana. Parts of that now look even more promising than they did. The droughts in North and South Dakota seem to be somewhat relieved, but we're still forecasting you're not going to be above normal, even if you get extra precipitation. So something of a relief based on that. The southern Great Plains looks just as bad as it always has in our forecast period. And the central Great Plains, northern Colorado and Nebraska continue to look good. Oops, last forecast really looks the same as the previous one. Something of more of a relief in the North and South Dakota, but the rest of that pattern has stayed similar. The difference between the above and below normal is now very minimal. And as we go with time, the difference between the max and the min gets narrowed because there's more and more real precip in the forecast. So by the time we get to early June, pretty much we can say what's going on, I think. It's my analysis. We have this historical NDVI data that goes back to 82. This is the data from like 82, the 90s, 80s and 90s. Interesting, you see all those red areas in the northern Great Plains. Northern Great Plains had a number of severe droughts in that period, which was the positive PDO cycle. That's a 20-year cycle. And that actually tends to be not so good in the northern Great Plains. And in the southern Great Plains, we actually had variable, but more likely above normal precipitation. In 97, we shifted to negative PDO, and the pattern shifted. Then you see the northern Great Plains had typically good production, lots of big blue areas, where the southern Great Plains, we had massive droughts for, actually, if you look at 2011, 12, 13, it was really bad for multiple years, and that continued. So PDO potentially has a prediction. If it's negative, PDO and ENSO are negative, we tend to have really dry conditions in the southern Great Plains. If it's positive, you tend to have good conditions. And the northern Great Plains is not particularly well correlated. So potentially PDO cycle tells us something about what's going to happen. Maybe better than the forecast from the Weather Bureau. Okay, grass productivity, we used NDVI. simulated actual evapotranspiration and observed plant productivity to develop these statistical relationships to predict plant production as a function of actual evapotranspiration. So these three data sets we put together, developed the GrassCast model, and then we used the observed weather data and predicted weather data to then make forecasts of plant production for all of the Great Plains counties. We have the potential to make better forecasts, possibly by connecting it to sea surface temperatures, but we're always going to have a problem of getting good forecasts. And the last meeting I was at the Weather Service talking about this stuff, it wasn't very promising. So.
Thanks, Bill. This is great. Questions from the group out there for Bill?
Yeah, feel free to unmute yourself and go ahead and ask if you have a question.
Hey, hi, this is Doug Cluck. Can you hear me?
Yes.
Hi, just a quick question. Bill, have you talked to Marty Hurling and Ben Livney and a few other folks down there in Boulder about the Missouri Basin, which basically is the northern Great Plains, and some of the skill or non-skill that they've found in terms of well, the state of the modeling as it stands today?
I haven't talked specifically to them. It was the meeting I was at in May, particularly about that flash drought in the northern Great Plains. That was one they really missed well, and they don't, why, I'm not certain. I got a lot of understanding about why that happened.
Well, yeah. I can tell you why. It's
okay.
The why is because we don't forecast very well up there. I mean, it's really that simple. And unless we're in sort of an El Nino La Nina situation, and it's the cool season, we're going to have a lot of trouble.
Okay.
And there's been a couple papers done about the predictability, if you will, of the northern plains and such, especially in the warm season. And to be blunt, it's not very good unless what I just said, we're in a La Nina or El Nino, and it's sort of the cool season of the period. Now, you point to PDO and a few other things, and there has been some other work done by a few other researchers in terms of predictability on the decadal scale, but golly gee, I don't know anything in the annual scale that is very helpful. So your comments about difficulty are spot on. So it makes this a difficult task at best.
Well, we've done, as part of what we're doing, is we've done on an annual basis the PDO ENSO signal, and in the Southern Great Plains, it really has a fairly strong. We're using our NDVI data for the last 40 years as a basis for talking about what's happening, and we do show that it's fairly strong predictive in the region where it works, which is Colorado, New Mexico, and Texas, but it doesn't extend very far north. I mean, that predictiveness, as you're saying. So.
Yeah, just too much variability up there.
This is Dennis.
Yeah.
Have you been seeing how the Mike Hobbins stuff been incorporated with some of the forecasts and where using the eddy? Yeah. And that seems to be, promising, and how to incorporate that into some of the forecasts.
Yeah, you know what? And like all these tools, and this is just not just, but it's another tool in the toolbox, if you will, that have to be taken sort of together. And the key, I guess, is to sort of figure out each year, or I don't know how soon or how early people start making decisions on the ranch, but I imagine they're pretty early, and they either cull herds or move cattle or whatever they decide to do at different times. But the idea would then be to use this along with eddy, along with whatever the models are saying in terms of how the climate's going to behave, and sort of mishmash all that together. And we do that in our brains, sort of in an inexact way. I don't know the best way to mesh all this together, other than to present it in sort of a over and over again, maybe on a monthly basis at a key time of year, to those producers that care about it.
Right, and that was sort of why we have this 3-level forecast, because that's what we had the last fall, we went to all of the county, not all the counties, but all of the regions in the Great Plains and talked to the NRCS range specialists and ranchers typically at these meetings. And what they, first of all, said that if you tell them something by the middle of May, they can potentially manage or use that, particularly in the northern Great Plains. Even by the end of early June will be useful to them, which our forecasts at that point are actually starting to get pretty accurate, because the precip that happens early is more important than the precip that happens later. So that's why our forecasts become more accurate. So we can at least hit them in part of the time period, which is useful. And one of the, there's another thing we discovered that we're going to use this year is if you look at the MODIS NDVI data on May 15th, the southern Great Plains, we can predict with a 0.7 R-squares what's going to happen for the season based on the early season NDVI, which is a really interesting, another way that we can forecast or help forecast. So NDVI current values, particularly in the southern Great Plains, are predictive. Northern Great Plains, what happens in May 15th doesn't help you at all. There's no correlation.
But yeah, just I don't mean to belabor the point, but there is a key season, as you all know, north to south, south to north. I'm sure it changes a little bit. But if you don't get the rains or the proper weather or whatever at that time, you're pretty much in trouble for the rest of the year, or you're well off for the rest of the year. And
Right.
And it tends to be May and June, generally speaking, that the rains either come or they don't.
Well, that's what our statistical analysis, and that's all just what you're saying is incorporated in our models, and that's why the accuracy by the time we get to the middle of May and early June, we're pretty much on what's going to happen at that point because of exactly what you're saying.
We have a question in here on chat from Trevor. How are these maps received by ranchers? What are some of the reactions you've gotten to the below normal, normal, above normal splits? And have you heard about any particular approaches being utilized in response to different scenarios?
What we've had so far, I guess Danielle Peck is the one who gets the responses, or she's on, I haven't actually getting them directly on the website. The website is out there. She's the one that sort of gets that. Most of the responses we've had are from NRCS people that we train people how to look at these data earlier or last fall. And the responses we had have been mainly with NRCS people saying, is this correct or not? Am I off in our forecast? And pretty much the people in the different states have been sort of verifying what was happening, those major patterns that I talked about. We haven't had, or I haven't had, and I don't know that Danielle would be the one to really answer this question from a specific ranchers, but we have from the NRCS range specialists mainly getting confirmation of what's happening. That the southern Colorado drought stuff has been verified. Colorado is crazy. We're just like I-70 splits the state in half, and it's great in the north and dry in the south. And you go into Nebraska and Colorado, northern Colorado and Wyoming, and things are really nice. Everybody's happy. And then you have a sort of a mixture in the North Dakota and South Dakota region. And then Montana, verification of what we were predicting. So what we have had is verification of some of our predictions, not much on actually using them to change their management yet. So.
Okay.
So Bill, one of the things that Robin O'Malley and I have been talking about in the coming years is to start an assessment analysis of sensitivity of things like production to climate change projections. So try and do a 2050, 2100 outlook. It seems like your model, at least your algorithm here, we could actually provide the climate projections across a suite of GCM downscaled products and actually start looking at the potential vulnerability to different landscapes across the region. How difficult would that be?
I think what we have is readily available to taking forecasts. And we actually have two levels of data. One of them is this detailed level, the Grassland model predictions and the statistical connections and all of that. But having this historical NDVI data for all of the Great Plains, and then this verification that it's actually being measured on the ground, we have this sort of long-term patterns in the connection between the climate and the AET. And one of the questions, Dennis, we've been talking about for a while is this temperature effect. What we found is AET is the most correlated. When we looked at the temperature effect, we don't find whether it's a dry year or a wet year, wet or dry matters, whether it's hot or cold doesn't seem to affect our correlations very much at all. What we do find is in the northern Great Plains, the water use efficiency is higher, and that's because it's colder there. So the mean productivity in that region is more productive for the same amount of actual water loss. So that there is a temperature connection to the mean, but when you look out on interannual variability, we can't find any temperature effect. So it's curious that we get a long-term impact on the temperature should reduce productivity in theory. And if you look at the long-term means, if you increase it 2 degrees C, you should be reducing productivity in the Great Plains. But that's sort of based on taking what's happening in what do you call it, Texas and Oklahoma and extrapolating it north. But it's curious that we don't see a temperature effect on interannual, but we do see a temperature effect on the means.
Okay, well, thanks, Bill.
Can I do one more?
Yeah,
Is
one
that,
more. Go
okay.
ahead.
When you talk about, I think this will be a quick one. When you talk about next year rerunning GrassCast at a finer spatial resolution, is the idea to do it within the same region and for the same time period to look at how variable things are within counties, or is it kind of just looking at going forward with the finer resolution?
No, we'll do the same things,
Okay.
but with the finer spatial scale weather data driving us.
Okay.
So we're looking at doing it maybe at a 5-10 kilometer scale using our interpolated weather data, not necessarily changing our NDVI connections. We're just going to use finer scaled weather, which would get you where you have rainstorms that hit you, and where you have this finer scale weather pattern.
All right, great. Thanks, Bill.